name is Michael DeLay. I'm an application scientist with IDEX Health and Science. Today, I'm going to talk a little bit about optimizing the choices of catalog and custom optical filters when working with the Semrock optical filters from IHNS. So the topics that I'd like to include would be making an introduction to Semrock, to talk a little bit about something called precise edge placement, which is an option that one can use to improve the definition of spectral edges. Then there'll be a short discussion of results from the new Kola Deep spectral measurement system. And following that, there'll be a feature demonstration of the simulation tool SearchLight, which is used for optimizing choices of filters and sets. Following that, a brief mention of cost drivers, factors that affect filter costs. And then finally, a note on working with Semrock in the context of medical devices using optical filters. So Semrock was founded in 2000. The basis for the foundation has to do with offering hard-coded filters, optical filters with hundreds of layers. And that was in the context of what were then standard soft-coded filters with only tens of layers. The technology that was brought to bear was sputtering, the sputtering method for deposition, which yielded the densest films and the best filter performance. And based on this, the first of the Brightline catalog filter family was offered in 2002-03. The new availability of the sputtering methodology and the hard-coded designs resulted in many innovations, which have resulted in more than 24 patents being issued to Semrock. Semrock joined IDEX Corporation in 2008 as part of IDEX Health and Sciences. So there are three key aspects of Semrock filters that I think characterize the optical filters from Semrock. The first is the use of manufacturable specifications, that is, specifications that correspond to the actual delivered filters. The second is the fact that what is delivered are filters that meet those specifications. In other words, every filter that is shipped meets specifications. And the third is that Semrock is at pains to prove that the filters meet those specifications. And I'll discuss some of those aspects here. So starting with specifications, Semrock, as I said, provides manufacturable specifications, meaning that the filters will meet them. They are, of course, they're not really design specifications in the sense of limited to design. They are actually what is delivered. So the illustration to the right here can be used to understand some of this. The orange lines indicate constraints on spectral performance of this exciter-emitter bandpass filter pair. The left one, for example, shows a red line which corresponds to the guaranteed minimum bandwidth of the filter, which is essentially the pass bandwidth in nanometers over which the transmission will be 90%. It is a little different, as you can see, from the full width half maximum. The other constraint lines include this OD definition here, and then the necessity of a separation in OD between these excitation and emission pairs so that there's a kind of what is called a crossover point, and of course others. And the thing that is interesting about these is that they are different. The difference between these key points, like for example, this edge up at the top left here, and the center of what's actually coated is the presence of a manufacturing tolerance. So there's a manufacturing tolerance here, there's one there, and so on. these manufacturing tolerances are very well understood by Semrock, and Semrock builds into the specifications the fact that these exist, so that the filters that are delivered will therefore always adhere to these because they lie outside the zone of manufacturing tolerance. So that is illustrated in these two spectra, one for an excitation filter and one for emitter filter, coated over a number of years in 40 different batches using different coating machines. They all show the characteristic steep edges and flat top with high transmission, and the amount of excursion or tolerance is well contained in both of these filter examples. So continuing on this discussion of spectral edges, there is a situation that has arisen recently that allowed us to improve things a little bit further, and that's called precise edge placement. So the idea here is that there are situations in which there's spectral crowding. So in this case, there's the Psi5 excitation emission spectra here, and then the Psi5.5 excitation emission spectra here. The emission and excitation spectra, of course, overlap. And the task is to be able to use a single dichroic to separate these two. Well, you can't really do that because there is so much overlap. But the point is that the LWP dichroic is meant to transmit the Psi5.5 emission and reflect the Psi5 emission. Of course, there's overlap, as I said. So in this case, the solution is to use some methodology which will allow some spectral unmixing. The spectral unmixing, however, is confounded to some extent by the manufacturing tolerance inherent in the position of this filter. If the filter moves back and forth from machine to machine, that will require, that means there's inevitably going to be machine-to-machine difference. So in this case, we have implemented what we call precise edge placement, in which this edge here, the location of this 50% point on the dichroic, is held within better than normal manufacturing tolerance over the duration of the production. So this is a handy capability that could be used in these kinds of cases to, say, eliminate the need for calibration under certain circumstances. So now let me move on to another aspect of what I was mentioning before, that is the three key points about what Semrock does in terms of its filters, and that is the issue of measurement of what is difficult, namely steep edges and deep OD, or optical density. Such filters really do make it difficult for standard spectrophotometers to correctly measure the parameters of optical density and steep edge position. A typical kind of issues that we're on across would include the noise floor shown here. That is the level at which one can no longer distinguish OD, let's say 7 from 7.5. Then the presence of sideband measurement artifact associated with non-monochromatic probe beams, and then finally the cutting of corners here associated with non-zero cone half angle in the probe beam. So these are issues that confront all of us in this kind of metrology. Semrock has decided to build a solution that will push the envelope a bit further, and that is the Kola Deep spectral measurement system. It's named after the Kola Deep, which is a very long, very deep borehole that was created during the Soviet Union on the Kola Peninsula. The Kola Deep system can measure blocking to OD9 and beyond across the UV to near infrared, and can resolve edges steeper than 0.2% relative to the edge wavelength. That is over a range from K equals 90% to OD7. So to show the kind of performance that's achieved here, one can look at this max line filter at 248.6 nanometers. and look at the theory, which shows the edge, the spectral edge on both sides of the laser line, and the Kola Deep system measurements, which track it extremely well down to about OD7 or so. And then one can also see that the standard spectrometer will show results that deviate starting around OD3. An analogous kind of measurement on a 532 nanometer razor edge ultra steep LWP filter is shown here. And in this one, there's a orange line that indicates that OD6 is required at this point. The measured data and the theory both show that this is achieved, and the Kola data go on to indicate that OD9 is now is reachable here. And again, the spectrometer, standard spectrometer, tends to deviate starting around OD3. So that wraps up my discussion of the Kola Deep system. The next thing I'd like to share with you is a brief feature demonstration of SearchLight. So SearchLight is a free web-based tool that appears on the website searchlight.semrock.com. And it consists of essentially an engine which models the behavior of a microscope, an epi-illumination microscope, using components that each have some responsivity or sensitivity or light output as a function of wavelength. So using a set of these parameters, one can then convolve the behavior of this and obtain numbers such as the amount of signal arriving at the detector. And another one that it's able to find is the level of what we call noise, which is, it's called light noise in specific. And it is essentially something that reduces contrast. It is, in fact, the reflected light from the specimen or from a cover slip, which reflects back up without changing wavelength, of course, and then passes towards the detector. So I'll just show you briefly some qualitative use, and then show you a little bit about the calculators that one has available, which help to optimize spectral performance. So on this screen, I'm now showing SearchLight, a SearchLight screen. The left-hand panel shows the things that you can select to populate the display with, the spectral display. Fluorophores are here, filters, filter sets, light sources, detectors, and then one is given a folder where one can store one's own data. Here's the spectral display, and then on this side is the legend with the individual components. So there's a GFP spectrum, that GFP filter set here. Then there's the GFP spectra appear here. There's a camera spectral responsivity, and there's also a light source spectrum for an LED. So this is this can be plotted in as an OD or in transmission, and it gives you sort of a reasonable qualitative feel for how well these things go together. But if you want to look at something quantitative in order to optimize something, then you can use it in that mode. And here's another example with a little different situation. Here we have an M-Cherry filter set here. So that's the excitation, the dichroic in dotted line, and the emission filter quite wide. And the spectra of two fluorophores, M-Cherry on this side and Alexa 647 on that side. And in this case, what happened was that the customer who uses this filter set complained that they were getting too much bleed through from the Alexa 647 into the M-Cherry channel. It's qualitatively understandable that because this excitation spectrum overlaps with the excitation of the M-Cherry, that there would be excitation, and then that emission with this spectrum would be captured by this clearly too wide emission bandpass filter. But the question is, can SearchLight illustrate quantitatively the problem and then propose a solution based on some kind of numerical situation? And in fact, that is possible. That uses these things called calculators. And I'll show you a couple here. So what I'm showing on this calculator here is, it's called M-cherry in the M-cherry channel, which means how much signal from M-cherry ends up in the M-cherry channel. And to find that, I select the filters to correspond to the M-cherry set. The fluorophore corresponds to M-cherry fluorophore, and then we have, of course, the light source in the detector. And then we have some kind of quality indicator here, which is the fluorescence signal level. That is sort of a small number. I can perhaps show you what it is, 8.4 10 to the minus 7 milliwatts. And then in the panel below it, the calculator below it shows what happens if you use Alexa 647 as the fluorophore instead of M-cherry. That tells you how much bleed through you get of that. And in fact, 3.9 or so compared to 8.4, it's a very significant amount of bleed through. So what one has to do then is propose an alternative and prove that it would work. The alternative is to choose a filter like this, which does not extend as far as into the red. And so we can now compare and see how situation is here. And in fact, the fluorescence signal is significantly reduced from 8.4 or so to 5.6. But on the other hand, the crosstalk or bleed through is now very greatly reduced. So this is now no longer, would not be expected to be a major issue at this point. So let me go back to the PowerPoint and continue. The next point I'd like to talk about briefly are cost drivers for custom filters. So when one's thinking of optimizing filters, one can also think about trying to reduce cost by choosing aspects of the optical system that could result in reduced cost. So the cost drivers include parameters such as the spectral edge steepness. Edge steepness is obviously a cost driver because one needs more layers to obtain a steeper spectral edge. More layers means more coating time, and that drives the cost. Blocking or a lot of coating in the infrared range is a driver because a layer to perform a certain function in the infrared at say 1600 will be 4 times as thick as that corresponding layer at 400 because they scale with wavelength. And then the issue with cone half angle is that having a larger cone half angle means that we have to modify the filter design in order to prevent the spectral edges from shifting with wavelength, because that makes the edge less steep. And that is therefore a cost driver. Less of a cost driver are things like the wavefront requirements, the blocking into the longer wavelengths, let's say, and the area, though area is obviously a factor because the bigger filter will consume more of what is coated. And then on the lower end, one has things like non-standard substrates and cosmetics, which are really quite a bit less significant. So finally, I want to just quickly mention the question of using catalog filters when one's building prototype devices. This is normally not an issue, but when one is thinking of an optical device which might be regulated by the FDA, which would require that the specifications remain frozen, then we have the situation where a catalog filter might not be ideal because catalog filters can be modified or may be modified over time in order to improve performance and so on. The solution is in general to transition from catalog to a custom filter based on that catalog filter whose specifications remain locked. And that's also convenient, perhaps at that point, to think about the volume production and cost discussions. So that's the end of my presentation on this optimization. Thank you.